An aircraft engine producing over 100,000 newtons of forward thrust touches down at more than 250 kilometers and within 2 seconds that same engine is pushing air the opposite direction, helping stop tens of tons of aircraft on a runway that suddenly looks far too short. That naturally raises a question. How does a jet engine built entirely to push an aircraft forward suddenly work backward? And this is where the most common misconception needs to be cleared up right away. A jet engine does not spin backward to reverse thrust. The turbine, the compressor, the entire core keeps rotating in exactly the same direction it always does, at the same enormous rotational speeds, driven by the same combustion process. What changes is not the engine's rotation. What changes is where the air is allowed to go once it leaves that rotation behind. Reverse thrust is a mechanical redirection system, and it involves aerodynamics, hydraulics, electronics, and strict flight crew procedure, all sequenced to the second. It is not a switch that simply flips the engine into reverse the way a car's transmission does. It is a carefully engineered sequence of physical barriers and computer checks, and an error in that sequence, or a reverser that deploys at the wrong moment, can turn a routine landing into a serious emergency in a matter of seconds. Preparation for reverse thrust actually starts well before touchdown. During final approach, the flight crew arms the reverser system, but arming is not deploying. Arming simply tells the aircraft's systems that reverse thrust is authorized and ready the instant certain conditions are met. Until those conditions are met, the system sits in standby, mechanically locked and electronically inhibited, waiting for confirmation that the aircraft is actually on the ground and not still flying. This is critical because activating reverse thrust while airborne, even for a fraction of a second, can destabilize the aircraft, violently disrupt airflow over the wings and tail, and has in fact caused fatal accidents in aviation history. That single possibility is the reason the entire system is built around layers of confirmation, rather than a simple pilot command. If you're interested in understanding how complex machines actually work beyond simplified myths, this is exactly what we focus on. The first requirement, and the most fundamental safeguard in the entire sequence, is confirmation of weight on wheels. Modern airliners use sensors built directly into the landing gear struts that detect compression, the physical proof that the aircraft's full weight has settled onto the runway. Only once this signal is confirmed does the system allow the reversers to move at all. Everything downstream of this single signal depends on it. This safeguard exists because the consequence of an early deployment is severe enough that redundancy isn't optional here, it's mandatory, and most aircraft actually require signals from multiple wheels agreeing simultaneously before the system proceeds. The moment weight on wheels is confirmed marks the true start of the reversal sequence, and here is where the actual mechanism differs completely from what most passengers assume. On the majority of large commercial engines, reverse thrust is achieved through what's called a cascade system, and understanding it means picturing the engine's outer skin as a moving mechanical shell rather than a fixed tube. A set of translating sleeves on the outer engine cowlings slide backward along tracks, physically exposing rows of curved vanes underneath that were hidden during normal flight. At the exact same moment, blocker doors rotate into position inside the engine's bypass duct, forming a solid wall that seals off the normal rearward exit path for the fan's airflow. Instead of exiting straight backward and pushing the aircraft forward the way it does throughout every other phase of flight, that same enormous volume of air is forced outward and forward through the cascade vanes at a calculated angle. That redirected air pushes the aircraft in the opposite direction. The engine core itself never reverses, never changes rotation, never runs backward in any sense. Only the airflow's exit path changes, guided entirely by mechanical doors that move into place and then retract when their job is done. On some aircraft, particularly certain older or smaller jets, a different design called a clamshell or bucket-type reverser is used instead. Here, two large hinged doors curved to match the shape of the exhaust nozzle physically swing closed behind the entire engine exhaust. Rather than exposing side vanes, this design blocks the exhaust path completely and deflects the full exhaust stream forward and outward in one motion. Either way, whichever mechanical approach a given aircraft uses, the underlying principle is identical. Block the natural exit, force the air a different direction, and Newton's third law does the rest without needing any change to how the engine itself is producing power. But there's a trade-off most people don't realize, and it's the reason reverse thrust is never treated as the primary braking method. Reverse thrust is most effective immediately after touchdown, at high speed, when there's still enormous airflow moving through the engine to redirect. As the aircraft slows, that effectiveness drops sharply, because the amount of air being pushed through the system decreases along with speed. That's why reversers are described in flight training as an early-stage tool, useful in the first critical seconds but not something crews can rely on all the way to a stop. On a dry runway, reverse thrust typically contributes only a portion of total deceleration, concentrated almost entirely in those opening seconds after the wheels touch down. Pilots are trained to stow the reversers well before reaching taxi speed, both to protect the engine from unnecessary wear and because continued use at low speed can actually cause the engine to ingest its own exhaust, along with loose debris from the runway surface, back into the intake. Only after all of this does the electronic control system fully take over the fine details of the process. Modern aircraft use a FADEC, or Full Authority Digital Engine Control, to manage the exact thrust level produced during reverse operation. The crew selects reverse using the thrust levers, physically pulling them into a distinct reverse position, but the computer behind that lever calculates precisely how much power to command based on runway length remaining, current aircraft weight, and the deceleration rate needed to stop safely within the available distance. This prevents the kind of asymmetric thrust that could otherwise pull the aircraft toward one side of the runway if the two engines produced even slightly different amounts of reverse force. And here's the problem that makes this system necessary in the first place. No human reaction time is fast enough to manage that kind of asymmetry manually at landing speed, where a fraction of a second's delay can mean meaningful directional drift. That's exactly why FADEC exists, continuously monitoring both engines independently and correcting instantly if one produces more reverse force than the other, long before a pilot could ever perceive the imbalance. The same computer also enforces limits that protect the engine itself, preventing reverse thrust from being commanded at a power level that could damage internal components, and it constantly cross-checks sensor data from multiple sources so that a single faulty reading can never trigger an unsafe command on its own. Environmental conditions matter here too, and they change how heavily crews rely on this system. On a contaminated runway, whether wet, icy, or covered in slush, reverse thrust becomes especially valuable because unlike wheel brakes, it doesn't depend on tire-to-runway friction at all. It keeps working at essentially the same effectiveness even when traction is severely compromised, which is exactly the situation where wheel brakes lose the most stopping power. That's why crews are specifically trained to lean more heavily on reverse thrust in poor weather, adjusting their entire deceleration plan and runway distance calculations before they ever touch down, rather than discovering mid-rollout that the runway offers less grip than expected. Dispatchers and pilots factor current runway condition reports directly into their landing performance calculations, and on genuinely poor surfaces, the planned use of reverse thrust can shift from a supporting role to one of the most important factors in whether the aircraft stops within the available distance at all. If something still doesn't go as planned, redundancy exists here as well, built into the certification standards every commercial aircraft must meet. If one engine's reverser fails to deploy, the aircraft is still certified to land safely using only the remaining reverser, combined with wheel brakes and spoilers, because reverse thrust was never designed to be the sole method of stopping the aircraft in the first place. It was designed from the outset to be one layer within a much larger, deliberately overlapping system, so that no single failure point can compromise the entire landing. Engineers refer to this as graceful degradation, where the loss of any one component reduces performance slightly, but never removes the aircraft's ability to stop safely within a certified distance. The key point is this: reverse thrust isn't the engine running backward. It's the engine running exactly as it always does, spinning in the same direction at the same fundamental speeds, while the air it produces gets physically rerouted through mechanical doors and angled vanes controlled by sensors, computers, and strict procedure at every step. That layered redundancy, weight on wheels confirmation before anything moves, Cascade or Clamshell mechanisms doing the physical redirection, FADEC managed power preventing asymmetry, and environmental adaptation built into crew training, is exactly what makes the process so reliable across millions of landings every year. So, a jet engine doesn't stop an aircraft by reversing itself in any literal sense. It stops it by redirecting the same forward force it was already producing, at precisely the right moment in precisely the right amount, using a sequence that leaves nothing to chance. One of the most interesting details connected to this is what actually happens if a reverser deploys by accident while an aircraft is still in flight, and why engineers built an entire separate mechanical and electronic safety system just to prevent that one specific failure from ever occurring. And if you enjoyed the video, don't forget to subscribe to the channel and leave a like.